Assalamu alaikum. So this is the June 2022 paper, and I'll just be going through, how I would personally solve it and perhaps some advice on what you should be thinking about. So question one, a machine has a power of 750 watts and transfers 150 kilojoules of energy. So already I know I might have to convert during a time t. Which of the following expressions gives t in seconds? So you'll start with the equation, which is power is energy over time. The energy transferred is 150,000, so 150 times 1,000. And the times what you're trying to work out. So rearrange, I guess. So T is equal to E over P, which is 150 times 1,000 over 750 watts. Right, that's the power, which is C. Question two, a sphere falls through a viscous liquid as shown. Which row of the table describes the upthrust and the viscous drag on the sphere as it accelerates downwards? Well, it's accelerating downwards, meaning its speed is increasing. And I know as the velocity or speed increases, the friction or the viscous drag will also increase. So it's between A and B. Now we have to think about what's happening with upthrust. Well, what is upthrust? Upthrust is the weight of the fluid displaced, so mg, which is the mass of the fluid displaced, multiplied by g. And I know that the mass of the fluid displaced is the density of the fluid multiplied by the volume of the fluid displaced, which is the same as the volume of the object underwater from Archimedes' principle, multiplied by G. And I know that the density of the fluid doesn't change. The volume of this sphere underwater doesn't change. And G is just a constant. So upthrust is clearly constant as well. So the answer is B. Which of the following is a scalar quantity? Well, it's not force. It's not momentum. It's not velocity. All three of these have a direction. Whereas work done or energy transferred is a scalar. The graph shows the relationship between tensile stress and tensile strain for a material. Which of the following gives the Young's modulus of the material? Well, I know that Young's modulus, E, is equal to stress over strain. And looking at this graph, that would be the gradient, right? Stress over strain would give you the gradient. So it's not the area under the graph. It's not the area, so it's not A or B. The gradient of the tangent to the line at the origin. Good. So it will be the gradient, and it will be the gradient of the straight line region. So the tangent to the line at the origin. So answer is C. A student determined the value 4G by dropping a metal sphere from rest. The student measured the distance fallen and the time taken for the sphere to fall. He obtained a value of 11.2 meters per second squared. Which of the following could explain the difference between the student's value and the accepted value, which is obviously 9.81? Well, to answer any question like this, you need an equation to help you understand what variables play a role. So we're talking about constant acceleration with initial velocity 0 because it's got from rest. So I'm thinking S is equal to ut plus half at squared, which is the equation for anything falling down with constant acceleration. And the initial velocity is 0. So I'm just going to say S is equal to half at squared. We'll make the acceleration the subject because we're trying to see which variables impact the acceleration. So A is equal to 2S over t squared. So how can I get a higher value for acceleration? Because that's what the student obtained. He obtained 11.2. Well, either I could have measured a larger displacement, or I could have measured a smaller time, right? Either you divide by a smaller number or multiply by a larger number. So let's see which of the following options gives either of these. So it says the first option, the air resistance was not negligible. Well, if there was no air if there was air resistance, then actually the way you should think about this is the forces acting on your sphere are not only weight, there's weight down, but there's also air resistance opposing the motion, meaning your new resultant force is your weight minus the air resistance. So your new F-res, which is equal to your mass times acceleration, is now smaller. And I know that acceleration is force over mass. So a smaller resultant force will, of course, give you a smaller acceleration. You got a larger acceleration, so it's not A. The student's measured distance was greater than the actual distance. Or looking back at this equation we just wrote, that will give you a higher acceleration because there's a larger displacement. So there'll be a larger acceleration. So the answer is indeed B. A rocket is accelerating horizontally due to a constant resultant force. The mass of the rocket decreases steadily, steadily meaning at a constant rate. So not exponential, rather linear. So which graph shows how the acceleration of the rocket could change? Well, I need, just like the previous question, I need the expression for acceleration to help me answer this. I'm going to write A is equal to F over m for Newton's second law. And I know that the force is constant, because it says due to a constant resultant force. However, the mass keeps decreasing steadily. And the smaller mass, you're dividing by a smaller number, acceleration is going to increase. So if the mass is decreasing steadily, the acceleration will increase steadily. And the only option that shows this is B. So as the mass decreases, the acceleration is increasing. Okay, two arrangements, P and Q, of identical springs are subjected to the same tensile force. When one spring is subjected to a tensile force F, the elastic strain energy for the spring is E. Which row of the table gives the total elastic strain energy for each arrangement? So the equation for elastic strain energy is equal to half force multiplied by extension. Now, in both arrangements, the same force is applied, as you could see. So the force doesn't change. So we are looking at the extension. In the first scenario, the springs are attached in series and they're receiving the same force. However, the length is doubled, meaning the extension will also double. So we're going to write EL is equal to a half F 2 times the extension. So clearly there's a factor of 2 here, meaning you're going to, the total elastic strain energy will be double the initial amount, because this is equal to 2 times the initial elastic strain energy you expected. So it's either C or D. Now, in the second arrangement, well, we need to know when the springs are connected like this, they're going to receive half the force each, or you could think about it, they're going to extend by half the amount each. And because they're extended by half the amount, it will be half F extension over 2, which is equal to half the elastic strain energy. Because the extension is half, it will have half the amount of elastic strain energy. So the answer is B. You don't need to know too much about series and parallel other than what I've shown here for springs. The velocity time graph shows the motion of a particle with constant acceleration. PQ and R represent the magnitudes of each area shown. Which of the following expressions gives the total displacement of the particle? It's asking for displacement, which is what you get from a velocity time graph. And you should know it's the area under the graph. So the total displacement, well, first of all, it had a negative velocity here, right? Meaning it had a negative displacement. So the area above the graph, in this case, will be the initial displacement traveled. And then here, it has a positive velocity, so it's traveling a positive displacement. And the total displacement will give you R minus Q, right? The positive displacement minus the negative displacement, which is D. If it asks for the total distance traveled as opposed to displacement, then it would just be R plus Q as shown here. But that wasn't the case, so be careful. Okay, a cyclist rode along the slope at a constant speed. The increase in vertical height of the cyclist was delta H. the slope was at angle theta to the horizontal axis. Already they've given me a side and an angle. I know that I might have to use some vector resolving some trigonometry. We'll see. The forward force of the road was on the bicycle. Sorry, the forward force of the road on the bicycle was F. So there was a F going along the slope. And air resistance was negligible. So this F is your resultant force. Which of the following gives the work done by the cyclist? Well, we need the expression for work done, which is force times distance. You need to be aware that the force and distance have to be parallel to each other for this to work. Okay, so I need a distance parallel to where the force is, i.e. I need this distance here. So what I can do is draw this triangle out. It's a right angle triangle, angle theta. You're trying to work out x, the hypotenuse, and you're given the opposite. So you're going to start with sine theta equal to opposite over hypotenuse. So that's equal to delta H over X. You want X, right? You want the hypotenuse, the distance parallel to the force, which is X is equal to, so just swap these two around, delta H over sine theta. Now substitute this in for your distance. So your work done is equal to force multiplied by delta H over sine theta, which is D. Okay, when compressed by a force of 50 newtons, so this is compressed, not extended, so just keep that in mind. A spring had a length of 12 centimeters. When compressed by a force of 70 newtons, the same spring had a length of 7.1 centimeters. Which of the following expressions gives the stiffness K of the spring in newtons per centimeter? It's always worth first looking at the expressions, just so you kind of have a general idea of what form you want it in. Well, stiffness K is equal to F over your extension or compression. Well, you initially had a force of 50 and you added 70 newtons. So your force you've exerted, the additional force you've exerted is 70 minus 50. And the compression is the initial minus the final length, which is 12 minus 7.1. And that gives you B. Okay, a disk of mass M is held stationary by a force F exerted by a magnetic base as shown. The free body force diagram for the disk is shown below. The two forces shown are equal in magnitude and opposite in direction. Give two reasons why these forces are not a Newton's third law pair. So let's just do a quick recap of what are the conditions for a Newton's third law pair. Well, the first is it has to be a pair of forces. So two forces. The second, they have to have the same magnitude. They have to be in opposite directions. The fourth is it has to act on separate objects. And finally, it has to be the same type of force. So let's have a look. Which of these does it satisfy and which does it not? So is it a pair? Yes, it is a pair. Do they have the same magnitude? Yes, they do, because the length of each arrow is the same. Are they in opposite directions? Yes, they are. So from the first three, we're expecting, okay, it should be a Newton's third law pair. However, when you look at number 4, is it acting on separate objects? No, it's acting on the same object. So this is not satisfied. And is it the same type of force? No, because you have mg, which is weight, and F, which is a magnetic force. So you've got force of gravity and force due to a magnet. They are not the same type of force. So you're going to say something like, because it is acting on the same object and because it, they are not the same type of force. Maybe even specify weight of the force or mg of gravity where as F is force due to the magnet's repelling or magnetic force. You could phrase this how you want. So the magnetic base has weight W and rests on a horizontal table. Complete the free body force diagram below for the magnetic base where it says it rests on a horizontal table, meaning there is no resultant force. Forces are balanced vertically and horizontally if there is any. So yeah, there's weight acting on your magnetic base. I know there's also the reaction force, but also there's a Newton's third law pair of this force F. Because the magnetic base exerts a force F on the disk, therefore the disk has to exert the same type of force, right, on separate objects, so on the magnetic base, with the same magnitude and in opposite directions. So actually, there has to be a force downwards of the same size as this F over here, same magnitude in the opposite directions. So there's a Newton's third law pair for this force F. So I'm going to repeat this one last time. So the magnetic base exerts a force F on the disk. Therefore, the disk exerts a force F on the magnetic base in the opposite direction of same magnitude. So there's going to be a magnetic force F here. And of course, we know the forces are balanced and there's the reaction force, which draw it a little bit longer and label it R. Good. The reason I drew it a bit longer is because the sum of the lengths of these two vectors has to equal this one to show that it's in equilibrium. Okay, when an increasing force is applied to a steel cable, it will eventually reach its elastic limit. State what is meant by the elastic limit. Elastic limit is, I guess, the maximum force such that the steel cable will not return to its original length once the force is removed. Good. This is your definition for elastic limit. I wrote steel cable because you always have to contextualize the question. So when it says stay what is meant by the elastic limit, it means stay what is meant by the elastic limit in this scenario. So the steel cable. The elastic limit of a steel cable was reached when a force of 13.4 times 10 to 6 newtons was applied. The extension was 0.126 meters. The length is 6 meters. The cross-sectional area is 9.6 times 10 to minus 3 meters squared. Calculate the strain of the cable at its elastic limit. So strain is equal to the extension over the length. The extension is 0.126. The length is 6 meters, which gives you 0.021. Strain is dimensionless. It does not have a unit because you could think about it. This has a unit of meters. Extension has a unit of meters. The length has a unit of meters. Kind of like cancels out. So yeah, I'm going to say 0.0210 and keep it to 3 significant figures, just because every value I used in my calculation was also to 3 significant figures, and you always want to use the lowest number of significant figures used in your calculation. Calculate the stress in the cable at its elastic limit. Well, stress is equal to force over the area. The force is 13.4 times 10 to the 6 newtons. The area was given as 9.6 times 10 to the minus 3, which gives you 1.40 times 10. If I round to 3 significant figures, 1, 2, 3, 4, 5, 6 times 10 to the 9. either pascals or newtons per meter squared. So yeah, that will be your answer. Don't forget the units, you will drop a mark. Okay, a colt hook is attached to a smooth door by a screw as shown. The diagram below shows 3 of the forces that act on the colt hook when a colt is hung from it. The weight of the colt hook may be neglected. Add a labeled arrow to the diagram to show the additional force required for the colt hook to be in equilibrium. We need to know there's 2 conditions for equilibrium, and that is no net force and also no net moment. So there can't be a resultant force either horizontally or vertically. There cannot be a net moment either clockwise or anti-clockwise. These must be satisfied for any system in equilibrium. So I noticed there's a force upwards and there's a force downwards. So vertically, there is no net force. However, horizontally, there's a force to the right. So there must be a corresponding force to the left to keep in equilibrium. Now the question is, where do you place this force? Do you place it here, 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 here? Well, to answer this question, we look at the second condition, which is there has to be no net moment. If we take the pivot to be here, notice there will be an anti-clockwise moment thanks to this weight. So now we need a clockwise moment to balance that out. So you'd have to draw your reaction force. And it's a reaction force. Why? Because there's 2 surfaces in contact. One's pushing against the other. The screw is pushing against the wall. So the wall has to be pushing back against the hook. And I drew it below. So I've now added a clockwise moment. That's just going to rotate it clockwise. This rotate it anti-clockwise. So now there is no net moment and there is no net force. Just be careful that you don't draw it too far down, like here, because this is no longer in contact. It's no longer touching the wall. And for a reaction force to take place, the 2 objects have to be in contact. So this would not score you both marks, but the first one would. So yeah, draw it like this and you'd get your 2 marks. So it says if too many cots are hung on the coat hook, the hook will rotate and pull the screw out of the door. Point P is the position of the pivot as shown. The maximum horizontal force from the screw is 150 newtons. The mass of one coat is 2.6 kilograms. Deduce whether a person could hang more than 2 of these coats from the hook. We're looking at this. They're giving you forces and perpendicular distances. So you know that moments is involved. And to deduce whether he could hang 2 or more coats, you need to know what is the maximum anti-clockwise moment that I'm able to provide before it exceeds the clockwise moment due to this force. So let's do moments and start by saying that your moment is equal to force times distance. And we know that moments clockwise equals moments anti-clockwise. We'll start with our clockwise moment, where P is the pivot. So it's going to be the horizontal force from the screw, or the maximum horizontal force from the screw, which is 150. So 150 newtons multiplied by the perpendicular distance, which is 0.9, shown in the diagram, times by 0.9. And that's equal to your anti-clockwise moment, which is the force. Let's call it force F multiplied by the distance, 2.5. And I'm trying to work out what is this maximum force that I'm able to, provide before it's no longer in equilibrium, before there's an anti-clockwise moment, because the weight of the coat, or F, is larger. So we'll rearrange and we'll say that F is equal to 150 times by 0.9 over 2.5, which equals 54 newtons. So this is the largest force, the largest weight of coats that you could possibly have before there's now an anti-clockwise moment. So let's see, how many coats can 54 newtons accommodate for? So to do this, we need to know the weight of one coat, which is just mg. So mg is equal to 2.6 times 9.81, which gives you 25.506 newtons. So now we're going to do the maximum force over the weight of one coat, which gives us 2.12 blah blah blah. Okay, so of course you cannot have 0.12 of a coat. So the maximum coats you could have is 2. So you're going to say therefore plus 2 coats maximum.